This is a problem from Putnam 2019, B2. We're given a finite trigonometric sum, and then we want to work out the limit of this sum over n cubed. I'm going to present it in two different ways. First way is that somehow I want to turn it into a kind of telescope function series, which is not immediately obvious when you have some sine and cosine square, but motivated by this known fact that half times 1/3 plus 1/3 times 1/4 all the way. When you can rewrite it into plus 1/3 minus 1/4, then you can cancel out the majority of the terms, right? Approaching half in the end. So if we can somehow rewrite it into some kind of 1 over cosine square alpha, where alpha is this angle, beta is this angle, cosine square beta, maybe multiplied by some constant in the end, if we're missing some term in here, then we're fine. So as we calculate it, see what it turns out to be. Cosine square beta minus cosine square alpha. So up to this step, we're going to apply the double angle formula. Turn this cosine square into half of 1 plus cosine 2 times beta. Likewise, minus half of 1 plus cosine 2 times alpha, all over cosine square alpha, cosine square beta. So this is equal to, I'm just going to move this move this 2 down here. Cosine square alpha, cosine square beta. And half just cancels out. Right, this half of cosine half, so half comes down here. Cosine 2 beta minus cosine 2 alpha, that's what we have. So up to this step, we're going to apply the formula which can turn this sum of two trigs into the product of two other trigs. To be specific, cosine x minus cosine y is equal to cosine half of x plus y plus half of x minus y. That's exactly the same as x minus cosine half of x plus y minus half of x minus y. You can easily check that this is equal to exactly y. So now we have cosine angle sum. Cosine this angle times cosine this angle minus sine this angle, sine this angle. So here minus, then you have plus. Cosine, cosine plus sine, sine. Cosine cancelled out. This negative sign, there's positive, negative. So twice negative. Sine, sine. X plus y. Sine x minus y. So x, y. That is 2 cosine square alpha, cosine square beta. And negative 2 sine half of x plus y, beta plus alpha, sine angle difference half, x minus y. X minus y. X half of x minus beta minus x. Beta minus alpha. X, y, half, yes. So cancel out the 2 here. Remember, there is a negative sign here. So if you look at this alpha beta, alpha plus beta equal to this term, right? This. So the only term we're missing here is this negative sine beta minus alpha. Sine beta minus alpha. Beta minus alpha is just pi over 2n. So all we have to do is to multiply then divide by the same term. So somehow we can turn this inside, we could call it summand. This summand is equal to, it's denoted as b and k. B and k, like I said, we multiply negative sign, then divide by negative sign. So we say negative sine beta minus alpha, like I said, is pi over 2n. Has nothing to do with k anymore. In the end, we can just factor it out. So then we say negative sign. So this whole thing, we just treat alpha beta as this and that. So this whole is equal to this difference. So yeah, 1 over cosine squared, copy it, cosine squared, k minus 1 pi over 2n minus 1 over cosine squared k pi over 2n. This negative side here. So when you apply the sum, k goes from 1 to n minus 1. Immediately we have a telescope down here. The only difference is k minus 1k, right? Just differs by 1. So ultimately the majority of the terms cancel out. The only term that we are left with is just first term and last term. First term, get finite sum equal to, copy this one down. First term, k equals 1, 0, cosine 0 is 1. Last term, n minus 1, n minus 1. Cosine squared, n minus 1 pi over 2n. So after we work out this expression for this finite sum, now we want to turn this cosine into sine, right, by using half pi minus this angle. Right, so half pi minus this angle, right, and this n minus times pi over 2n, half pi already cancelled out with the half pi, minus minus plus pi over 2n, right, so negative 1 sine pi over 2n multiplied by 1 minus 1 over becomes sine square pi over 2n. Right, then we divide by n cubed, right? N cubed. Then take n to infinity. Right, first term, what do we have here? So this term negative, n cubed sine pi over 2 plus 1 over n cubed, also sine also cubed, pi over 2n. Right? So again, so this sine, we already know that limit sine over x, sine as x approaches infinity, is equal to 1. Right? Or we sometimes say sine x is asymptotically equivalent to x as x approaches 0. In other words, this time angle is pi over 2n. So whenever you see this, you can always replace it with that. as n approaches infinity in terms of multiplication and division, right? Except plus and minus. So if it's multiplication, it's fine. So we can immediately just simply work out pi over n, right? Plus n cubed. Replace it with pi cubed 8 n cubed. Right? So immediately pi n squared plus, it doesn't matter. So in the end, this term approaches 0. So this term, of course, pi cubed 8, right? N cubed gone. So in the end, we approach just this term. And the second way is to use Taylor expansion. As we all know, nearby 0, we can write sine x as x minus x cubed over 3 factorial, so on and so forth. Using little o notation, x power to the power of 4. Right? That's piano remainder of Taylor expansion. The meaning of little o, again, is that if you can write f of x as g of x times h of x, where limit of g of x as x approaches some a or 0 perhaps equal to 0, then you can say f of x is little o of h of x as x approaches some number. Right? So meaning f of x approaches 0 faster than h of x, because you can treat little o as a function approaching 0 as well. So in fact, f of x is a infinitesimal of higher order compared with h of x. So in this case, I mean, we don't even need this term. Don't even need that. All we need is plus little o of x squared. Right? Because the second term is 0 because the constant is 0. But we still write little o of x squared because there's a second term here. So this term approaching 0 faster than x squared. So in this case, the reason I only write down those 2 terms instead of 3 terms is because when I expanded into 3 terms, in the end, it turns out that many other terms were did not play a major role, right? Could be omitted. So that's why, so before we replace sine with, we have to change cosine to sine. So for cosine, k minus 1 over 2n can be written into sine half pi minus this common denominator. All right, half pi, 2 pi over 2n. 2n pi over 2n. Half pi, n pi minus this, n minus k plus 1 times pi. Half pi, yes, half pi, n pi over 2n, half pi. Cosine k pi over 2n is sine half pi minus this angle. All right, so half pi, n times pi, n minus k pi, n minus k pi. But the thing is that we have to sum from 1 to k from 1 to n minus 1. Right, k from, so if we change k, n minus k into I, And then I should sum from n minus 1, n minus 2, all the way to just 1. So, in other words, basically it's the same thing, right? So again, we can also replace n minus k here as well. So, but what can we do about this one? Right? What can we do about it? So this implies that k is equal to n minus I. Again, we replace every k with in terms of I. So this integrand, this finite sum, the inside summoned, call it bk, bnk, bnk. First of all, I want to rewrite the top sign 2k minus 1 pi over 2n is simply sine 2n, 2k, 2 times k, 2n minus 2i minus 1 pi. 2n times pi over 2n is just pi, negative sign. Negative 2i, negative pi, negative become positive. Ultimately, should be positive. 2i plus 1 over 2n, right? So now it's simple. Now this finite sum, this summoned, inside summoned, b and k. Top we have sine. Now everything becomes I, right? Every k becomes in terms of I. Sine 2i times over 2n. Sine squared. It becomes n minus k becomes, like I said, becomes I pi over 2n. Okay, sine squared. No, cosine k1, sine n minus k. I plus 1 pi. So this becomes this. I pi 2n. So we successfully rewrite the inside summoned into this everything in sine form. Changed all the I into k's. So apply the Taylor expansion now. Right? Every sign can be written into, like I said, I just need those two terms. So this is x 2k plus 1 times pi over 2n. So little o of x squared, little o of x squared. Right? But x is kind of, very complicated, right? So constant k, can consider it as constant before we do the sum, right? K is some constant, then square everything. But I say we can just write it as 1 over n squared times little o of. Right? Everything else is just constant. Using this step, I'm not going into details, but this is why, the definition. As long as we can rewrite fx into some function approaching 0 times hx, then we say fx is little o of hx. Little o is this term approaches 0 faster than this term. Right? Other constant doesn't matter. Times some constant, just throw them away. Doesn't matter. So this square times this square. Inside square we have, again, k plus 1 times pi over 2n. I need this one. Little o of, like I said, disregard all the constant. Just 1 over n squared. Likewise, k pi over 2n plus little o of 1 over n squared. Now, gradually you will see that why we only need those two terms instead of 3 or more terms. So when you square, right, we have to keep in mind what main term, what major terms we need, and what other terms can be ignored, can be omitted. Right? First of all, this term is important, right? Square this one, and do not throw away the constant. Right? Still keep them. So copy down the top. 2k plus 1, 2n plus little o, 1 over n squared. Bottom, square this one, k plus square, pi square, 4n squared. And square this term, little o of 1 over n to the power 4. And 2 times this and that. Little o of this times that. Right? According to this definition, we can just simply multiply those two terms and write little o in front. But again, disregard the constant now. Right? Just 1 over n squared. Little o of 1 over n cubed. There we have little o of, after squaring this term, little o of 1 over n to the power 4th. We can just combine everything into little o of 1 over n cubed. Simply, right, combine, because little o of 1 over n to the power 4th, right, that's approaching 0 really, really fast. We can just put them all in this basket. Right? It can be easily verified. I'm not going to go into details. So this we have in here. Likewise, square this term. 4n squared. I need to keep everything, all the constant here. Like I said, the others doesn't matter. Square this, multiply this by that, times 2, constant doesn't matter. Throw everything into the basket of little o of 1 over n cubed. That's it. So now we worked out the b and k, the summand, to be this form. We continue multiplying. Right, we copy down the top. 2k plus 1 plus little o 1 over n squared. The bottom, we need this multiplied by that, right? Keep the all the constant. K squared, k plus 1 squared, pi to the power 4. Also 16 n to the power 4. Right? This is our main term. Right? When you multiply the other terms, like this multiply this little o, right? This when you multiply by little o, just disregard all the constants. Just focus on 1 over n squared, right? 1 over n cubed. So 1 over n to the power 5. When you multiply this to that, same thing. And finally, this little o to this little o. 1 over n to the power 6. Throw everything into the basket of little o of 1 over n to the power 5. Right, disregard everything else. This can be easily verified. Right, I'm not going to get into the details. So gradually you will see that, okay, that's two terms is all we need, expansion. Especially when you divide by n cubed. But before that we perhaps do the sum. Right? But when we do the sum, it has nothing to do with n. The only thing changing is k. Right? N cubed can be multiplied into it. Right? So an is this sum. Right? Then an over n cubed. Right? Put n cubed inside. K from 1 to n minus 1. like I said, you just put n cube inside, right? Put it on the bottom, right? On this bottom, right? The sum end, right? Simplify with this term, and also simplify with this term. So this all of a sudden becomes k squared, k plus 1 squared, pi to 4. 16 times n only, little o. This multiplied by n cubed, you only have 1 over n squared. Now, at the top we copy down. Pi over 2n plus little o of 1 over n squared. Right? Then, after you work out this sum, you take n to infinity. So this equal. This time we multiply everything, both top and bottom, by the reciprocal of this term. So this term will turn into 1. Just 1 plus little o of something. Right? Just focus on 1 over n. The reciprocal is n times this little o of 1 over n. Disregard all the constants. Likewise, this term multiplied by the reciprocal of this term. You have 8 over pi cubed. Then you have 2k plus 1, k squared, k plus 1 squared. This little o times by reciprocal of this term. Like I said, same reason. Just consider this is 1 over n. Right? So multiply by n, little o of 1 over n. Then we can say an over n cubed, that is equal to, first of all, sum, k is summing. This one has nothing to do with k. Right? Factor this one out. 1 plus little o of 1 over n. Then separate this sum and this sum. This sum, factor out the constant. This sum, just 2k plus 1 over k squared, k plus 1 squared. The other sum, k goes little o, 1 over n, right? Okay. So this sum, when n approaches infinity, right? So in fact, copy this one down. Multiply. This we can just separate this into the difference of two terms, which is which is 1 over k squared minus 1 over k plus 1 squared. Right? When you common factor equals this one, right? Then you this multiplied by this minus this multiplied by that equals exactly 2k plus 1. Right? This is easily verifiable. Again, telescope series. Then this sum. So when you have n minus 1 terms, right? Every term is the same. Little o of 1 over n, right? Just little o of n minus 1 over n. Right? Same as little o of 1, because ultimately this will approach 1 as n approaches infinity. Right? Same. So ultimately, this telescope series is easily just first term plus last term. Everything else canceled out. First term, just 1. Last term, right? Substituting here. 1 over 1 plus little o. And 8 over pi cube. Like I said, first term 1. Substitute n minus 1 into here. So just n squared. 1 over n squared. In the end. All right. So little o of 1. So when n approaches infinity, right, this whole thing approaches 0. So this approaches 1. This approaches 0. This approaches 1. Right? This little o of 1. Little o, like I said, approaches 0. Right? Still approaches 0. They all disappear. All disappear, right? As except, right, this approaches 1. Right? This just approaches 0. This approaches 1. The only thing